This is going to be the last lecture of the first part of the course. And before we start, a couple of announcements. So as you know, the midterm is next week, February 9th. Sorry, that should be March 9th. Sorry. March 9th. And you'll be here in the usual place at the usual time. Because of the homework of the midterm, there will be no homework given out this week. So what I'm going to do is post the solutions to a couple of problems, maybe 3 or 4 problems from the textbook that cover the material that we're going to see today, or at least that we're going to see in the first part of the lecture, so that if you want, you guys can practice on your own, and then you'll have the not only the answer, but actually the detailed solution of the problem, so you can check it against your own computations if you choose to do that. And that way you can get if you want, you can get some practice on what we'll see, at least the first half of the lecture, which will be part of the midterm. What we'll see in the second half probably is not going to be part of the midterm, so then you'll have a homework on that after the spring break. Questions about the midterm? I'm sure you guys are all fired up and ready. Right. So we'll cover chapters 1, 2, 3, and 4. Today we're going to finish up the stuff in chapter 4. We'll start with some of the things in chapter 5, but I don't think I'm going to hold you guys accountable for that for the midterm, since we're going to just see a little bit of the material. Probably doesn't make sense. So let's say chapters 1 to 4, 1, 2, 3, and 4. Okay. And the midterm questions are going to be in the same spirit as the homework questions. So, try to make you guys think a little bit. So you can bring calculators if you have them, and or computers even, for basic computations like logarithms and things like that. So if you need anything beyond that, like Q functions, I'll give you a table, or I'll give you the values that you need. So don't worry about that. But if you have calculators handy, bring them on. So. No, you can bring your book. I don't want you to just memorize stuff. I want you to understand things. And yes, you can bring whatever you want. It's not going to help you. No, I'm hoping it will. Okay. Any more questions about the midterm? All right. It shouldn't be more than 2 hours. Okay? Okay, so yes. The question is how many problems? I don't know yet. I'll put it together over the weekend, so as many as you can do in 2 hours. No, I don't know, but it'll be similar to a homework set, shorter probably. I'll try to have like a problem for each of the topics, pretty much. At least one problem for each of the main topics. Okay? Any other questions? Okay, so we're going to finish up chapter 4, and I guess what we'll start with is a quick revision of what we saw last week, up to the point where we ended, and then we'll finish up that part. And then whatever time is left, we'll start with some of chapter 5, so you can build a little bit of a pingle before the spring break. So last week we talked about information theory, this discipline created by or initiated by the work of Shannon, and we saw that the key notion that Shannon came up with was this notion of capacity, right? So the idea that for any power level there is a certain capacity such that if you choose the rate to be below that capacity, we can make the probability of error as small as we want by using coding. Okay, so that's the key idea he came up with. And so then people have spent a lot of years developing codes, better and better codes. And that's a topic that we're going to treat in the second part of the course. We saw that this reduction of error probability through coding entails that we add redundancy and dependencies in the data And it entails that we use these long blocks of data. And so as we let the blocks become longer and longer, we can make the error probability smaller and smaller. Okay? So we need this notion of very long blocks for information theory to be applicable. Then we went through derivations of the capacity for several channels. So we started with a very simple unfaded channel with additive white Gaussian noise. And so in this channel, the gain, this G, is constant over time. So it's just some fixed quantity. And we saw that the capacity of this channel, which was formed by Shannon, is equal to B, which is the bandwidth of the signal, times the log of 1 plus gamma, where gamma is the signal-to-noise ratio, which is the ratio between the signal power and the receiver. So we have P sub T is the transmit signal power. So P sub T times G is the receive signal power. And B times N sub 0 is the receive noise power. So the ratio between these two powers is the signal-to-noise ratio. And so log of 1 plus gamma times B is the capacity in bits per second. This log is in the base 2, which is usually how we're going to do things. Oh, what else here? We show some examples. Then we moved on to capacity of channels with fading. So we started with the flat faded channel. So in this channel, now the gain G is a function of time. So we can regard it as a random process. And we'll always assume that this process is stationary and ergodic with a distribution that depends on the type of fading. So typically Rayleigh fading, for example. So then G is going to be exponential, and the square root of G is going to be Rayleigh. That's a typical value, but it could be also Ricean or Nakagami. We saw that computing the capacity of these channels is quite more involved, and usually it's done in some limiting cases, so using these idealizations. So there were two idealizations. One that was a limiting idealization for fast fading channels, which was this ergodic idealization, where we assume the channel changes a lot during the code word. So we get to see all its values taken with certain probabilities. And then the other is the exact contrary, which is the idealization for slow fading channels, where the fading is about constant for a code word, for one of these coded blocks. And then it may change between different blocks. So this is this quasi-stationary or block fading model. And these are just useful mathematical idealizations which allow us to do some analysis and get some intuition. In practice, what you find is always something that's somewhere in between, but hopefully it'll be close to one of the two so that these answers are meaningful. Okay, so we saw that in fading conditions, the capacity is highly affected by what's known about the channel. So there were 3 different scenarios that we considered in terms of the channel state information. So the first was CDI, channel distribution information, where the exact value of the fading is not known by anybody. So all that the receiver and the transmitter know are the distribution, is the distribution of this random process. The second case, much more interesting, was the receiver CSI, where the transmitter still knows only the distribution, but the receiver now knows the actual randomization, so it tracks the channel at all times. And this is what most of the systems that commercial systems do. There's a third case, a little more challenging, which is where also the transmitter has the CSI. Okay? So in this case, both track the gain of the channel at all times. With fading, the SNR is a function of time. Gamma itself depends on I now. We saw that with CDI, distribution information, the capacity is essentially unknown. So it's a very difficult problem, which is why all the commercial systems spend a lot of effort and a lot of complexity and processing to track the channel. So there's a lot of stuff in your cell phones that just tracking the channel at all times, just doing that. So that's this case. So in this case, there are 2 notions of capacity depending on which of the idealizations we're looking at. So if we look at the fast fading ergodic idealization, we have the channel capacity or ergodic capacity. If we look at the slow fading channels, we have this outage capacity. And as I said before, the capacity is of course defined for the cases that are in between these two. There's just no tractable. but the capacity itself does exist. So this is a pictorial representation of the two idealizations. This is the ergodic. So these are code words, and the ergodic has a lot of variation within a single code word, whereas the quasi-static has essentially no variation over one code word, although it may have it between code words. Yeah. It's kind of an artificiality, but it's a useful one. Okay, so for the first case, in the ergodic scenario, the capacity is given by the expectation of this log of 1 plus gamma. Right? So you can think about it as at any point in time, the channel has a capacity log of 1 plus gamma, and so you get to see all these different values of gamma, and this gives operational meaning to the expectation, and so what you end up with is with an average. So that's the answer in this ergodic case. We saw that using Jensen inequality, one can prove that this capacity is always smaller or equal than the capacity of some fictitious equivalent channel that had no fading but the same average gamma. Okay, so the point of this is to notice that that fading essentially can only reduce the capacity with respect to a channel that has no fading but the same power. And this is true when the receiver has CSI, but the transmitter does not. Okay, so essentially the idea is that the worse the fading, the more the reduction in capacity. We went through an example here, which we're not going to repeat now. Okay, now for slow fading channels, we have this outage capacity, which is a little more involved, right? In this case, the transmitter doesn't know the channel, and so it has to choose a rate without knowing the channel. It only knows the distribution. So what it's going to do is going to choose a rate that it hopes for. Let's say it's B times log of 1 plus gamma min, right here, where gamma min is some SNR we're hoping for. We do that, we send the block of data, and now two things can happen, right? The actual gamma may turn out to be bigger than gamma min, in which case we're okay, so we can decode the data, and everything's fine. Or the actual gamma may happen to be smaller than this gamma min, and so our rate was too high, and so the data cannot be decoded because we exceeded the actual capacity, and so an outage has taken place, right? So the outage probability is therefore the probability that gamma happens to be smaller than gamma min. So the throughput, the average rate that actually gets through, is B times log of 1 plus gamma min. This is the rate that we send. Okay. Now, how often does it get through? Well, it doesn't get through with probability P out, so it gets through with probability 1 minus P out. So that's the throughput. Tells us how many bits per second actually get through successfully. Okay. Now, how do we find gamma min? How do we choose it? Well, it's a design parameter that depends on which kind of outage level is acceptable. So if we want a few outages, we have to choose a low gamma min. We have to be very conservative. If we can tolerate more outages, and that may depend on the application, right? If we can tolerate more outages, then we can increase gamma min and be more aggressive. So in order to maximize the throughput, we need to find an optimum gamma min, which can be done. We saw that the typical graphical representation of the outage capacity is by means of a plot representing this chosen rate, V times log of 1 plus gamma min, as a function of the outage probability. And there are a number of those plots in the textbook, such as 4.2 for the case of Remy fading. Okay, we went through another example here with a lot of detail. So that's about it for the case of receiver CSI. And then the last thing we saw is the capacity with flat fading and CSI at receiver and at transmitter as well. Okay. So in this case, since we know the channel of the transmitter, we can actually do power control and use the power over time in a smart way. So we can say, okay, at times where the channel is bad, we can just reserve the power and don't use it. And then we can use it when the channel is better, for example. We can do things like that. And in other words, we can control the power based on the knowledge of the channel in some clever way. So this is what we mean with the power adaptation. Or we can choose not to do that. We can just, even though we know the channel, we can just choose to transmit at a constant power P bar. right? Maybe because the amplifier doesn't allow this power control. That happens sometimes. So if we choose not to do that, if we send the constant power, then what we find is exactly the same that we had when there was only receiver CSI. So in this case, even though we have this information about the channel at the transmitter, since we're not using it, the capacity does not increase. Okay, so that's the main point here. The transmit CSI does not increase capacity unless the power is adapted. Okay, that's the main message. Now let's say we do adapt the power as function of the CSI. Now we have P now is a function of gamma, which is the state of the fading state of the channel, with the constraint, of course, that the average power has to be equal to some constant, say P bar, right? So if we use more power at the good times, but less power at the bad times, we have to keep the average constant. Otherwise, we're cheating. So now the SNR we saw is equal to P of gamma times gamma divided by P bar. Okay. So now how do we find the capacity? Well, we have to do a maximization, right? We have to, okay, so the capacity is given by this integration, which is an expectation. So this is an expectation of B times log of 1 plus gamma. It's the usual thing, right? Where gamma now depends on the power we chose, P of gamma. Now, how do we choose these P of gamma? Well, we have to maximize, so find the P of gamma that maximizes this integration, right? So of all the P of gammas satisfying the constraint, right, such that the average does not exceed P bar, of all these possible P of gammas, there is one and only one that maximizes this integration. That's the one we want to find. And as we saw, although we didn't get into it in detail, one can solve this problem using Lagrangian techniques. There's actually other ways, but this is the most common one. And this involves a little bit of math, and what comes out at the end is that P of gamma divided by P bar, for convenience, the optimum such P of gamma divided by P bar has this form. Whenever gamma is below some gamma 0 that we call the cutoff SNR, we transmit no power. So P of gamma is equal to 0. So these are the bad channel states, right? So when the fading is very bad, we just shut it off, don't transmit. Now, when fading is good, so when gamma is above this cutoff, we send 1 over gamma 0 minus 1 over gamma. Okay, so this is the mathematical form for the optimum power strategy. And if we plug this solution into this integration, what comes out is this modified integration, which now integrates from gamma 0 to infinity as opposed to from 0 to infinity, because below gamma 0, we're not using the channel, we're just shutting it off. That's why the integration doesn't go below gamma 0. And the remaining point is how to find the cutoff. So how do we find gamma 0? Well, we have to enforce the power constraint, right? We have to ensure this condition. We have to ensure that the power, right? So we have to ensure this condition, that the expected power is equal to gamma, to P bar. So that turns into this integration. And so replacing P of gamma divided by P bar by the optimum policy, what we find is this condition. So by solving this integration, this equation, this is an integral equation, we can find gamma 0. Okay, and now you put it in here, we can find the optimum power control. Okay. In general, this equation must be solved numerically if the fading is continuous. That's why in all of the examples and in the problem sets, you're using discrete fading function so that you can actually solve these as a summation. Okay, so it's a useful exercise. And in contrast with the case of only receiver CSI, in this case with transmitter CSI as well, the capacity may actually increase with fading. It doesn't always do, but it could. Okay, we saw a very useful graphical interpretation, a very popular graphical interpretation for this optimum policy, which is the water filling. So what you do is you take your channel variations over time and turn them upside down, and you treat this as a container. And then you pour water up to a level 1 over gamma 0. which is the 1 over the cutoff. In fact, here's the animation, right? So you do this. You turn the channel upside down and treat it as a container. You just put water up to 1 over gamma 0. And the level of water at each point in time tells you the value of P of gamma divided by P bar. Okay? So you can see here that this is a typical time where you're going to shut it off. So this is a bad fading, I guess here. And what you do is you just don't use the channel. Instead here, you're using a lot of power because these are good fading conditions. Okay? Okay, so we went through an example where we found the cutoff and then we found I guess the capacity as well. Right. Exactly. So this is, oh yeah, we also saw this. Okay, so that's the optimum strategy, the water filling. Now, there are suboptimal adaptation techniques that are actually very interesting, even though they're suboptimal. They simplify the procedure very much, so that's why very, very useful. So the first one we saw is this channel inversion. So what we do here is instead of doing the water filling, we do kind of the opposite. We invert the fading so that the transmitter and the receiver can see a channel that is essentially constant. So in water filling, what you do is you send more power when the channel is good. You send less power when the channel is bad. Or sometimes, if it's very bad, you don't even send any power. With inversion, it's the opposite. You send more power when the channel is bad and less power when the channel is good. And the goal is to make the channel look as if it had no fading. So you want to exactly cancel the fading so that the receiver and the transmitter can see a constant channel. That's the goal. So it's kind of the opposite of water filling. And the highest possible unfading level that you can support, the sigma, we saw is 1 over the expected value of 1 over gamma. Okay? And so B times the log of 1 plus this quantity is called the zero outage capacity. So this is the capacity of a channel that had no fading and an equivalent SNR given by 1 over the expected value of 1 over gamma. So this is practically appealing because it doesn't require any rate adaptation. So the coding, so you code over a channel that it has no fading. So it's very easy. It is as if, in fact, as if it was an unfaded channel. So the coding and decoding are very easy, but there can be a very high penalty. Oops. Sorry, guys. So the coding and decoding are very easy, but there is a significant penalty in capacity. In fact, for example, with rarely fading and just channels where the fading is very bad, what happens is that you cannot invert the channel. So this expected value of 1 over gamma is infinite. And so the zero outage capacity is exactly 0. So what this means is that the fades are so bad that you use so much power left to compensate for the fades, to invert them, that you have no power left to transmit when the channel is good. So essentially, the fades are so deep that you don't have enough power to compensate for them. That's what this means, the fact that the zero outage capacity is equal to 0. So the channel is not invertible, essentially. So there is a variation of this approach that recognizes this problem. So as I said, the problem is that the bad fading states are very, very bad. Now, the idea in this variation, which is the truncated channel inversion, is to say, okay, I'm going to give up on some of those states. So when the channel is very bad, I'm going to give up on it. I'm going to try to invert it when it's not too bad. That's the idea here. So again, we use this notion of a cutoff, gamma 0. We say, okay, when gamma is below gamma 0, channel is so bad, I'm just giving up. So I'm shutting it off, and I'm sending no power. Okay? Now, when it's above this gamma 0, sufficiently decent, then I'm going to invert it. And so I'm going to do the same thing I was doing for the channel inversion. Okay? So now we're going to have outages, right? Whenever gamma is below gamma 0, we have an outage. And so we have to choose this gamma 0 carefully depending on how much outage we can tolerate. So the sigma that we can support, and so the sigma that we can invert when not in outage is equal to 1 over this modified expectation. This E sub gamma 0 is a modified expectation which integrates from gamma 0 to infinity. So, a usual expectation integrates from 0 to infinity. So this modified expectation integrates from gamma 0 to infinity. That's what this symbol means, something that we just made up for convenience. So this is what it means. And so that's the level we can support, we can invert whenever we're not in outage. Okay? And so now we have this 1 minus P out, because we have probability P out of being in outage, times B times the log of 1 plus this 1 over this modified expectation of 1 over gamma. So it's the same thing we had for the truncated, except that the expectation is now modified, and we have this 1 over 1 minus P out outside. Okay? So now we can try to optimize this by finding the best possible gamma 0 so that this is maximized. And in fact, we went through that in this example here. And what we saw is that actually this strategy is pretty good. So it falls pretty close to the action capacity, and it's very interesting in terms of implementation. So it's a pretty good technique. Okay, we finished up by looking at some comparisons using plots that are in the textbook for the 3 types of fading: non-normal, Rayleigh, and Nakagami. Okay, so that's where we left it last week, and we're going to pick it up here now. Any questions first before we move on? Yes.
What they were explaining now, how do you calculate that gamma 2?
In this example? Okay, so I think we went through this, right? So this is this usual channel that had 3 states, right? This is the channel that had, okay, let me find it.
Is the same gamma 0 from the other?
Not necessarily, right? So right, so this is the, let me find the example. This is the one, right? We have three different gammas with probabilities 10%, 50%, and 40%, right? Okay. Yeah, and the gammas were, we computed them somewhere. Yeah, 0.83, right? We had 0.83 with 10% probability, 83.3 with 50% probability, and 353.3 with 40% probability, right? So now, in these discrete channels, usually you can put the gamma exactly at these different values, right? So here you can put, if you put it just over 0.83, so let's say 0.84, right? How much outage you going to have? What do you think? No, remember what you do, right? So you choose a cutoff, gamma 0, and now whenever gamma is below that gamma 0, that's an outage, right? Because you're not going to send any power. That means you're giving up on that transmission, right? So if gamma 0 is 0.84, in this case you're going to have 10% outage, right? Okay. So that's what we had in the example, right? Now, that's not the only choice, right? You can choose, now, any value that you choose between 0.83 and 83.3 is going to have the same outage, right? 10%. Now, when do we find a different outage? When we cross 83.3, right? So let's say 83.4, for example. Then the outage jumps to 60%, right? And there's another jump when you cross this point, and you're going to go to 100%, right? 100% doesn't make any sense. So you're going to have with 2 choices, essentially. Let me go back. In fact, 83.4, right? So this is one choice, and this is the other choice. Essentially, it comes down to these 2 choices, right? Now, if you compute it for the first case, what you find is this. And if you want, we can go over this. For the second case, you find a smaller value, so you choose the first. Now, the calculation for each of these two cases, right? So what you have to solve is essentially this. You find sigma, and yeah, because the third gamma is in outage. Yeah, so you do you compute this. Exactly, you compute that. So the capacity is given by that formula. Now, how do you compute this E sub gamma 0, right? Yeah, exactly. So you sum over gamma 1 and gamma 2. You sum over here, right? Yeah, so you do, in fact, we can do it. So you do 1 over gamma 1 times the probability of gamma 1, which is 10%. No, 10% is not being used. So, right, so gamma 2, which is what? Times 2.5, right? 0.5, right? Plus 1 over gamma 3 times 0.4, right? And this is 0.83, and this is 83.3, right? So that way you find... yeah, I'm sorry, yeah, the first one is not used. 83.4 and 53.3, right? So that gives you this expectation. Now you do 1 over this, right? And you do 1 plus 1 over this, compute the log, times the bandwidth, times 0.9, because the average is 10%. And that should give you 192.5, right? Now for the other case, it's even simpler, right? You just do this part here, and you redo the computation, and now the outage is 60%, so you get it at 0.4 times that log, and it comes as the problem. The reason it's worse is because the 0.4 kills you, right? So even though the algorithm gets better, the 0.4 outside kills you, and so you end up with 116. I'm sorry? Yeah, exactly. So at the end, what you find is that you should use the 0.84, right? Unless if the outage is, if the 10% outage is acceptable. If they tell you that you cannot accept them, imagine that I tell you, okay, do this example, but the outage cannot be more than 5%. Then exactly. Then you cannot use this gamma because you have 10%, so you have to be more conservative. So you may have to give up some capacity to secure outage sometimes. You have to use an outage gamma so that you're never in outage, right? So what would you use here? You have to use so you have to make sure that that gamma is always bigger than your gamma 0, right? So which is the worst possible gamma? Right, so you have to use a smaller gamma, right? Okay, 0.82, for example, right? My choice would be 0.82, right? Because it's as close as possible to 0.83. So it's just below it, right? You have to be below it, but you want to be as high as possible. So you go just below it, right? It's your choice. And it's going to be almost the same, right? It's going to be very similar in rate, but you have no outages. This is what happens with these. See, these type of discrete fading states are strange because they're step functions. So in reality, you always find, actual channels are always smooth, not discrete like this. But otherwise, you end up with integrations that you cannot solve. So in this case, you end up with summations. That's why it's a useful exercise to use with these discrete channels. But they're a little bit of an artificiality. Okay, but very good questions. So any other ones? Okay, so there's very little left, so we'll go over it and then we'll take the break. So the last part on this chapter is the capacity of frequency-selective channels. Okay, so far everything was flat fading, so everything was very easy. Now let's lift this restriction and allow for the fading to be frequency selective. Okay? So we're going to look at two cases. The first is frequency selective but time invariant. So you can imagine that as a channel that changes in frequency but is frozen in time. And the second case, and more general, is frequency selective and also time invariant. Okay, time invariant first. So consider a time invariant channel. And now, so the gain now is a function of frequency. So instead of function of time, it's function of frequency. And using the notation in the book, I'm going to call the square root of g, I'm going to call it h. Okay, just to be consistent with the textbook. But this way you can relate to what we saw in the flat fading case. Okay, so under time invariance, people always assume that there is CSI at the transmitter and at the receiver. Why? Well, if the channel is really frozen in time, the receiver can estimate it and then inform the transmitter, right? So use a feedback channel and report back. So if the channel doesn't change over time, we can, take it easy and just report back, feedback, and so everybody knows the channel. So let's say the total power that we have is capital P. And we need to find the optimum allocation of power, this time over frequency. So let's call it P of F. So P of F is going to be the power per unit of frequency. So it's going to be watts per hertz. So it's power density, if you want. Okay? Subject to the constraint that the sum of the power over the signal bandwidth is equal to P. Okay? So the integration over the signal bandwidth capital B of P of F times dF is equal to P. So we sum power over the entire bandwidth, and it cannot exceed P. So this looks something like this. We have a transmit signal X of I, where I is the time index, remember? It goes to a channel with frequency response H of F. And remember, the channel is time invariant, so it does not depend on I, it depends only on F. Now the signal is contaminated by noise, and that's the receiver, the received observation. So if you think about it for a second, you'll see that this problem is the exact dual of the flat fading time varying channel that we saw. Okay, so what before was time is now frequency. But other than that, it's the exact same formulation, right? So it's the same problem mathematically, except the time axis has now been replaced by the frequency axis. So the variation that we had in time now is variation in frequency. And so the solution is going to be, as you can imagine, very similar. It's going to be a dual solution. Okay, so what's the SNR at each frequency? Okay. So let's take a tiny little interval of frequency delta F. Okay. So how much power do we have on that little tiny frequency interval? Okay, so we have, let's say delta F is a tiny little interval of frequency. P of F is our power as function of frequency. So let's take an interval so narrow that P of F is constant. Okay, so P of F times delta F is the power on that little interval. And now how much noise do we have? By the way, this is the transmit power. Now this goes to the channel, right? So in the previous slide, this is what we send here. Now it goes to the channel. So it's multiplied by the gain, which is H of F, magnitude squared, since H may be complex. And now how much noise we have in that tiny little interval of frequency? Well, N0, which is the noise density times delta F. Okay, and so I can cancel these guys, and we find that the SNR around frequency F is P of F times magnitude square of H of F divided by N sub 0. Okay, where N sub 0 is the noise density in watts per hertz. So this is watts per hertz, this is watts per hertz, and this has no dimensions. So the whole thing has no dimensions, as it should. It's a ratio. Okay? I'm sorry? The question is, why is P being divided by the bandwidth? Are you jumping ahead, or you're jumping ahead, right? Okay, give me a second. I'll get there. Okay, so I'm still in the first integral, right? So let's formulate the capacity of this channel. Well, as usual, it's going to involve an log of 1 plus SNR, right? We know that. So at frequency f, it's log of 1 plus SNR at that frequency. And we just saw that the SNR around frequency f is this ratio over here, right? Which is this ratio over here. So log of 1 plus this is the capacity around frequency f. Now we integrate over the signal bandwidth, capital P. And now we have to maximize this over all possible P of f, right? So again, we want to find the best possible P of f is the one that maximizes this integration, subject to the condition that the total power is equal to capital P. Okay. Now to your question, careful with the units here. P is total power, so it's watts, right? P of f is watts per hertz, right? It's power per unit of bandwidth. So even though they both have P's, be careful because they're different units, right? So I'll take you through it. So we're still here, right? Any questions here on the first integration? Okay, everybody's cool with this. Okay, now before we move on to the second, let's define gamma of f, okay? So gamma of f is going to be the SNR at each frequency without power adaptation, okay? So imagine we take the total power that we have, capital P, okay? That's our total power, and we put it flat over frequency, okay? So what's the density on a tiny needle frequency f, right? It's P divided by capital P, right? So this is total power, this is total bandwidth. So P divided by B is the power per unit bandwidth if we assign it flat, okay? So this times the gain of the channel divided by the noise. Is the total power over our bandwidth of interest, right? So P divided by B is the power that each frequency interval would have if we put it flat. And be careful because in the book there is a typo around this area concerning this P and P of F. So I think you guys don't have the list of typos, right, on the textbook? And if not, send me email or Google it. There's a web page for the textbook, and it has a file with all the typos, the one that they found so far. And there is one around these derivations, and it has to do with this P of F. There is a B missing or something exactly on this point. So make sure you don't get confused by that. The slides are correct. I went through them carefully. So, so if something doesn't work for you, look up the typos because it could be that the typo is what's confusing you. Okay, so this is the SNR around the frequency f when the power is flat over the whole bandwidth. Questions here? You guys don't see these or not? Okay, so now let's substitute this gamma of f into the first integral, and just a simple variable substitution. It's going to give us the second integral. Okay. Now, if you look at this integral carefully and you check it against what we had in the flat fading time varying channel, you'll see that it's again is the exact same integration, except that time has become frequency. Okay. So the solution is going to be exactly the same with the proper variable replacement. So you can see the formula here is exactly the same water thing we saw before, right? So P of F divided by P over B this time is equal to 1 over the cutoff minus 1 over gamma F. Whenever at frequencies where gamma is bigger than gamma 0, so these are the good frequencies, right? And in the bad frequencies, we don't put any power. The same notion we had over time now is the same words over frequency. We don't put any power on the bad frequencies. We put more power on the frequencies that are good, on which the fading is good. And okay, I don't have a picture, but you can actually imagine the whole thing, right? You can imagine that this is now frequency. This is the response of the channel over frequency. Now you just water put over frequency. Okay? And this is what they do in DSL, for example. DSL channels. Some of you guys may have DSL at home. So in DSL, they do exactly this, right? They have a very wide bandwidth, so they measure the channel. The receiver reports back to the transmitter, which are the good frequencies, and the transmitter puts the power on the good frequencies, exactly in this way. Oops. Okay. So again, it's useful to simplify the channel sometimes and discretize it. We've been doing this so far already in the time domain. So it's also useful in the frequency domain. So imagine we have several blocks with gains h1, h2, h3, etc. Okay, with the same bandwidth each, for example, for simplicity. Then we can discretize the whole thing, right? We can define, instead of gamma of f, we can define gamma sub j for the jth block. And this is the same definition, right? It's p over b again, times h sub j squared. So it could be h1, h2, h3, whatever, divided by n sub 0, which is the noise density. And then the water filling looks like this, right? Tj divided by p is equal to 1 over the cutoff minus 1 over gamma j for the jth block. So the bad blocks get no power, the good blocks get more power. And the capacity is the sum over all the blocks whose fading is above gamma 0 of b times log of gamma j divided by gamma 0. So it's the exact same formulation we have here, except everything is now discrete. So the integration up here has become a summation now. So this makes the problem more tractable, as usual. And here's a baby example. Say we have 3 blocks, each one of 1 megahertz, with responses h1 equal to 1, h2 equal to 2, h3 equal to 3, and say we have a total power of 10 milliwatts. Okay? And the noise density is the usual 10 to the minus 9 watts per hertz. So using this formula, we can compute gamma 1, gamma 2, and gamma 3. And you can just plug the numbers, and you'll find that gamma 1 is equal to 10, gamma 2 is equal to 40, and gamma 3 is equal to 90. Okay, now, how do we find the cutoff? Well, we enforce the condition that the total power, so the sum of P1 plus P2 plus P3 has to be equal to capital P, which means that the sum of the Pj divided by capital P has to be equal to 1. Okay, now, we know that Pj divided by P has to move like this. So plug it in here. And now we solve this equation. And we find that gamma 0 is 2.64. That's the cutoff. And what does that tell us? That this block is not going to be used, right? So the first block, actually no, you cannot say that from here. You have to compute the gamma. So gamma 1, no, all the blocks are used, right? Because the cutoff is 2.64 and the gammas are all bigger than 2.64. So all the blocks are used. And you add up, so you compute the summation over the 3 blocks, and you find that the capacity is 10.93 megabits per second in this case. So it's the same exact procedure, but things are not happening in the frequency domain. Okay, it's not the time domain. Okay, any questions on these frequencies and active channels? Okay, it gets pretty easy. So the last thing we're going to see in terms of capacities is this frequencies and active time varying channels. So now we have channels that vary both in time and in frequency. So this is a very tough problem, and it hasn't been really solved yet. But you can approximate the solution pretty well. So we have a signal x of I going through a channel that depends on both frequency and time, contaminated by noise, and into the receiver. So the way to find an approximate solution here is by dividing the bandwidth into blocks of size the coherence bandwidth. So we want to find something like this. And the coherence bandwidth, remember, is the bandwidth over which the fading is pretty much constant in frequency. Okay, that's what that meant. It's the bandwidth over which there is little change in frequency. So we can discretize things in frequency by saying, okay, the coherence bandwidth is, I don't know, 100 kilohertz. I'm going to break up my bandwidth in blocks of 100 kilohertz. Each one is going to be pretty much flat, close to flat. So I'm going to idealize it as flat. In fact, there is a picture in the textbook that makes this point very well. So let me put it up. Here's an example, right? The actual channel is this smooth function, and the coherence bandwidth is this BC over here, right? So now we approximate the channel using 4 blocks. So each block is flat. And as you can see, this is an approximation because the channel is not really flat. But it pretty much captures the most important degree of changes over frequency. That's the idea. You break it up in frequency in blocks like this. And then remember that this is time varying, right? So this is like this is a particular point in time. Now, this changes with time. So over time, these blocks are going to go up and down. So you can imagine that this is a slice of an infinite sequence of time intervals on which this is going to change over time. So you can imagine this is a movie, for example. Right? So we have one particular frame of a movie. So that's the simplification we have to make this tractable. Furthermore, we are also going to assume that each block is not only flat, but independent of the other blocks. So the fading is constant over one block, and then is different from 4 different blocks. It's a simplification. So the solution under these simplified conditions is a 2-dimensional water filling in both time and frequency. Okay, so it's just a generalization of what we saw so far for time and frequency separately. And I'm not going to get into it in detail, but you do have it in the textbook at the very end of the chapter. And it looks like this, right? This is the capacity, and it's a summation over frequency blocks. That's the summation outside of an integration over time, right? So if you think about it, it's a combination of the 2 solutions we saw. The solution for the time variations, which is this integral, and outside we have the solution for the frequency variation in blocks, which is the summation. So both come together and bring us these 2-dimensional water filling. Yes. Yeah, the question is if you could do the same by discretizing time, okay, making blocks in time and not in frequency, right? And the answer is yes, definitely. I mean, there's no difference mathematically, there's no difference between time and frequency, except that time goes up to infinity and frequency goes within a finite bandwidth. But other than that, they're interchangeable. So you could do the exact dual of what I was explaining and have blocks in time and continuous fading in frequency. Right, so then you have coherence time, right? Blocks of the size of the coherence time, and then in bandwidth it could be continuous, right? You can definitely do that. And you could have actually discretization in both time and frequency. You can have blocks of the size of the coherence bandwidth that are constant over the coherence times and then change, right? That could be something for the midterm, for example. Very good suggestion. And what you cannot solve in general is the case where it's continuous in both time and frequency. In that case, some things don't quite work. That's why you have to discretize one or the other, essentially. But you can discretize one time instead of frequency, and you can discretize both. Discretize in the sense of making it into blocks. Definitely. And the way you find the cutoff is the same way. So the cutoff in this case is going to be one single cutoff, 1 gamma 0, for all the blocks in frequency and for all the time instants. Okay, so the cutoff is unique. So there's not a different cutoff for frequency or something, or per block or something. It's just one cutoff, just 1 gamma 0, and it comes out of this joint 2-dimensional optimization. So it's just a little more involved mathematically, but conceptually it's exactly the same. Okay. More questions on this? Okay, so that's about it. So let's go to a quick summary and then we'll take the break. Okay. So points to take home here are the notion of channel capacity. Okay. The mode capacity, you can use coding to drive the error probability closer to 0, as close to 0 as you want, by using betting on code words and using very sophisticated codes. information theory doesn't really tell us how to code. It only tells us which is the capacity up to which we can code. Okay. The key equation to remember in terms of capacity for Gaussian noise is log of 1 plus gamma, which appears everywhere. So this is the building block for all the capacity formulations that we have seen. Keep in mind these different notions of capacity, right? This ergodic regime and this outage regime for fast fading, slow fading. Keep in mind. What else? The point that when you have CSI at the transmitter, it's not any good if you don't adapt the power. So if you don't do that, you don't gain anything. If you do, then you end up with this water filling in time. And you can choose to use suboptical but practical filling techniques, such as inversion or truncated inversion. And things in frequency are resolved in the exact same way. So we find water filling. We could do truncation in frequency if you wanted to. We could do the same truncation that we saw in time in frequency also. Okay? And that's it for this chapter. So let's take a break, and then we'll start with some of chapter 5. Okay. Okay, so let's continue, and we're going to get into some brand new material, which corresponds with chapter 5 in the textbook. So this is a new set of slides that was posted on the web, I think last Friday. So hopefully you were able to access it. Okay, so modern systems are increasingly digital. In fact, digital is one of these overhyped words that is used in marketing today. Everything good has to be digital, even though most people don't even know what that means. But digital is good. And what does digital mean? Well, digital means that information is transferred in the form of bits. And bits is short for binary digits. Okay, for example, is radio digital? FM radio? Right? What do you guys think? Is it digital? Anybody? Non-digital, right? Radio is non-digital. We'll have digital radio very soon, but in Europe they already have it. But FM radio is not digital. Is TV digital? It's going there, right? But some of it is digital. Most of it is satellite is digital, but most of it is analog still, right? And the old cell phones were analog. Now most of you have probably digital cell phones. So a lot of times it does happen that the original source is not digital. For example, if I want to send you this PowerPoint presentation, that's digital. That's a bunch of bits in my computer. But if I want to talk on the phone, then my voice is not digital, right? So, or for example, a picture is not digital fundamentally, although a digital camera digitizes a picture. So what you do with the source that is not digital is you digitize it. And so we sample it and we quantize it. And thanks to a very famous theorem called Nyquist theorem, which probably most of you have seen before, a signal that is band limited, so has a finite bandwidth, can actually be sampled without loss of information, right? So you can sample a continuous waveform that has finite bandwidth, and then you can reconstruct it exactly as it was before, right? That's what Nyquist sampling theorem tells us. As long as we sample it fast enough, depending on the bandwidth. So the more bandwidth, the faster we have to sample. But if we sample fast enough, we can perfectly reconstruct the signal. So that's the beauty of Nyquist theorem, and that's the reason that we can digitize everything and reconstruct it with minimum loss in quantity. Now, to maximize efficiency, usually we take data and that we want to send, and first we compress it in order to eliminate redundancies and so squeeze out redundancies. Okay. Now, some of you may ponder about this and say, okay, why do we want to eliminate redundancies, right? We just learned in information theory that the key to good reliable transmission is to introduce redundancies, right? Remember I told you coding is a key element in reliable communication, and it entails dependencies and redundancies. So now I'm telling you that first, before transmission, you should squeeze out redundancy, right? So this may seem to you as a contradiction, but it isn't. So the point is that we squeeze out redundancies that we don't control, and then we reintroduce redundancies that we control through coding. Okay, so so the idea in communication systems today is to do exactly this. So you take your signal, put it into a box that compresses it, so it eliminates as much redundancy as possible, and then put it out into another box that is the coder, right? So this is coding that introduces redundancies, and then we send it to the channel, and the receiver will decode it. So this two-step process of eliminating redundancy. So the goal here, after this compressor, the goal is to have bits that are independent. So if you eliminate all the redundancies, we get bits that are independent, right? They're completely, no. There's no redundancy, so everything is independent. So the goal is to take your waveform, sample it if you have to, and then turn it using a compressor into independent bits, and then code those bits to make them again dependent, but in a way that you control, so that you can protect the signal against noise and fading. So as it turns out, this two-step approach, this separation of compression and coding, is actually optimal in some cases. And that optimality was shown, who else but by Shannon himself. So he's shown that in a certain number of channels, it is asymptotically optimal as the blocks become longer and longer to partition things this way. As opposed to having one single box here, you can have these two different boxes, one compressor and one coder. And then once we have the bits that are coded, we want to map them onto signals that we're going to send over the channel. So that's the wrong, so there's another box here, which is the modulator. It's going to map those bits into signals. Now, just to give you an idea, for example, so your cell phones work like this. Your cell phones, when you talk on the microphone, your voice is sampled and discretized, and then it's compressed very heavily, actually. So voice, uncompressed voice requires, for good quality, 64 kilobits per second. For example, when you use a landline phone, not a cell phone, that's what it burns, 64 kilobits per second. Now, the compressor, and this depends on the particular model, right, and the particular standard. So with the GSM, this is compressed down to about 10, 12 kilobits per second. So it's reduced by a factor of about 6 or 7. So those of you that have T-Mobile or single phones, that's what you're doing. And in CDMA, so if you have Verizon phones, it's compressed even farther, down to about 6 to 8 kilobits per second. And then it's re-encoded, and typically the rate doubles or triples going to the encoder. And that's the final rate that goes to the channel. Okay, so I'm sure that most of you are familiar with the zip program in your computer, right? When you do zip, you're compressing stuff, exactly. And the zip encoder is very good, in fact. The same thing when you have a picture that's in JPEG. Like if this is on camera, JPEG pictures are compressed, heavily compressed. Okay, so in this lecture, we're going to talk about, okay, so this box is something that we're not going to cover in this course. Okay, this is, I think there are courses here that deal with source coding. So this is compression. We're not going to talk about that. This, we're going to talk in about 2 or 3 lectures. Okay, there's a chapter in the book that covers coding. So we'll talk about that. And today, we're going to talk about this box, which is the modulator. Okay, this is going to take the bits that are coded and map them onto a signal that goes onto the channel. That's today's target, that M and the corresponding demodulator at the receiver. So the modulator maps bits onto the signal, and the demodulator or detector estimates which were those bits, given the received signal, which has noise and everything. So there are 2 classes of modulation, linear and nonlinear. The linear modulation formats embed the information into amplitude and or phase. Okay? These type of modulations are spectrally efficient, so they use bandwidth very well, but are more susceptible to noise and interference. And more importantly, they require linear amplifiers. Okay? Otherwise, the linearity is lost. So the amplifier has to be linear, otherwise the linearity is lost. And what's the problem with linear amplifiers? Well, they are more expensive than nonlinear amplifiers, and they are power inefficient. So linear amplifiers just waste a lot of power in heat dissipation. So that's the problem. So essentially, in these type of modulations, we have very good spectrum efficiency, but pretty bad power efficiency. The second class of modulations is the class of nonlinear modulations. And in this case, we embed the data into the frequency of the signal. So these modulations are spectrally less efficient. So they're more inefficient, but they are more robust to noise, and they can use nonlinear amplifiers. So these amplifiers are cheaper, and they're more power efficient. So they don't dissipate so much power into heat. So that's the trade-off, right? There's a clear trade-off between spectrum efficiency and power efficiency. So GSM phones, I think most of you guys have singular phones. We had a poll, I remember one day. So those use nonlinear modulations, okay, GSM. CDMA uses linear modulation. Now, that's what happened in second generation phones. There is a fragmentation, right? Some standards use non-linear, some standards use linear. Now, for third generation, all the standards under design use linear modulation. Okay, so there's a clear trend towards going to linear modulations, because what happens is the bandwidth has become more important than power. And so the bandwidth has become so expensive that it's more important to be spectrally efficient, even if you're more power inefficient. And so there's a clear move towards using linear modulations. And so we're going to focus in the course in these linear modulations. Okay, we'll say a few things about nonlinear, but mostly we'll focus on nonlinear modulations. So for today, for chapter 5 in the textbook, we consider only unfaded channels with additive white Gaussian noise, so no fading. And fading comes into the picture in chapter 6. So it's a two-step process, which makes it easier to deal with. Okay, questions so far, if any? Okay, so a little bit of fundamentals here on signal space analysis. The textbook has a lot of stuff here, so I've condensed it down to what we need for the course. You're welcome to go to the derivations in the textbook, which are like higher dimensional and stuff. But I think that what I've synthesized here is what you need. So this modulator transmits a sequence of pulses or symbols. We saw this before, of duration t sub s seconds per symbol. Now its symbol is going to carry capital K bits, so the data rate is going to be K over T bits per second, right? So we have K bits per symbol, and we have T symbols per second, so we have K over T bits per second. Now, there are 2 to the K possible groups of K bits, right? Each bit can be 0 or 1, has 2 values, so there are 2 to the K possible messages. So we're going to call this capital M, number of messages that each symbol can carry. Capital M is 2 to the K. And each one represents a different message. Now recall our passband representation. So we have capital M possible messages, so we need to be able to send capital M possible signals. So we're going to call each signal S sub I, function of time in general, and I going from 1 to capital M. Okay? And using our familiar passband representation, we can express S sub I of t as an in-phase component times the cosine of 2 pi fct, where fc is the frequency of the signal, minus a quadrature component times the sine of 2 pi fct. And I know that in the textbook, Professor Goldsmith uses 1 and 2 to indicate these dimensions. I'm going to use I and Q just to emphasize that it's in phase and quadrature. But note the correspondence so that you can relate the equation. And the reason is that she has a formulation that's more general than this, where she has more than 2 dimensions possibly, right? We're only going to use I and Q, so that's all we need. But keep this in mind if you want to relate to the textbook. Okay, remember that this is the passband representation. In the low-pass representation, these I and Q components are going to be the real and the imaginary components of the complex signal. Okay? Now, usually we'll want to give all the symbols a shape. Let's call it G of t, and we will see later why we want to give them some shape. And so we're going to have some unit energy function G of t. For example, a trivial one would be a rectangle, right? Imagine a rectangle that starts at 0 and finishes at capital T. That would be a trivial shape. As we'll see later, this is a very bad shape. But let's not concern ourselves with the shape so far. We're going to use some shape G of t. And so this SI of t can be expressed as SII. So this is the in-phase. So this is now a coefficient, the in-phase coefficient for the ith signal. So now this does not depend on time, it's just a coefficient. Okay. Times G of t. So now this G of t has the temporal shape. Okay. Times the cosine minus the quadrature coefficient times the same G of t times the sine. Okay. One could in general think about having different shapes for the in-phase and quadrature, but we're going to just consider always the same G on both. Okay, but in theory, one could have different shapes, but it's not really done in practice. So we're not going to consider that. Okay, that's the starting point for our derivations. Everything fine so far? Okay. Just for completeness, the corresponding low-pass representation is the usual complex signal. So it's the in-phase coefficient plus j times the quadrature coefficient times the shape g of t. Okay? So we can call these in-phase plus j quadrature. We can treat this as a vector, right? This is a complex number. We can treat it as a two-dimensional vector with two components, the in-phase and the quadrature. We're going to call this vector, and so I'm going to use the bold phase notation when I'm talking about vectors. So distinguish this is the vector for the ith signal. So we're going to call this ith vector the signal constellation point corresponding to the ith signal. Okay? And then the connection of all the capital M constellation points or vectors is going to define what we call the constellation. Okay, this is a very important notion that we'll be using for this part of the course, constellation. So here's an example. We have I and Q, and this is a particular point. This is the ith point, and so the vector goes from the origin to this S of I. Okay, so this is the real part is the in-phase component. Okay, and the quadrature part, the imaginary part, is the quadrature component. And now we can use some basic notions of vector space, Euclidean vector spaces. So the norm of a vector is the square root of the in-phase squared plus the quadrature squared. Okay, very trivial. And the distance between two different vectors is just, say, the norm of Si minus Sk is equal to the root of the square of the differences between the I and Q components. Okay, so this is all very simple, I'm sure. Questions? Okay. Okay, so the formulation we've seen so far applies to signals with both in-phase and quadrature components, so complex low-pass signals, or if you want, vectors in two dimensions, I and Q. So this constellation lie on a plane. Okay. Sometimes the signal may have only in-phase component. So as we know, this is suboptimal, right? Because we're wasting a dimension that we're not using. But sometimes for simplicity, people do that. And so in that case, the low-pass equivalent is real as opposed to complex. And the vector has just one dimension. So in this case, rather than being on a plane, the constellation lies on a line. So all the points are on a line. And we'll see some modulations that are like that. So they are suboptimal, but they are very easy. Okay, so that's the starting point for the derivations. Now, for each symbol, we're going to send a signal S of I, and what do we receive? We receive S of I of t plus noise. Okay, remember that for this derivation so far, there is no fading. There's only noise. We'll bring fading into the picture in the next chapter, but at this point there is no fading. So we receive the signal, if you want, times the gain, right? You can put the gain here, some constant gain, if you want to, plus some noise, Gaussian noise. Now the receiver needs to figure out which of the constellation points, capital M possible constellation points, was actually sent. That's the goal of the receiver, right? We have to figure out as accurately as possible which of the capital M points was actually sent. So each point corresponds to a group, remember, of k bits. Okay, so each of the capital M possible points represents a group of capital K bits. So by choosing, the receiver by choosing which point was actually sent is going to detect this group of k bits. Now, it is desirable to convert the received signal R sub t into a vector without losing any information, just to process it in an efficient way. So we can do that very easily because the noise emits its own Poisson representation, right? The noise is a complex signal, just like the signal. So we can express it as an in-phase noise times the usual cosine minus a quadrature noise times the usual sine. And likewise, the received signal R of t can be expressed as in phase times the cosine minus quadrature times the sine. And so putting the pieces together, we can see that the in-phase component of the received signal is equal to the in-phase component of the signal that was sent plus the in-phase component of the noise. And similarly, the quadrature component of the received signal is equal to the quadrature component of the signal that was sent, so the ith signal, plus the quadrature component of the noise. So in vector notation, we have that the vector ball phase R is equal to the vector S that was sent, so sub I, plus a noise vector. So all these vectors have an I and a Q component. Okay? And it can be proved that this vector is a sufficient statistic for the signal R of t, in the sense that it preserves all of the information about the signal that was contained in R of t. Okay? So, so this is very important. So there is no loss of information in going from a signal R of t to a vector ball phase R. Now, how do we do that, actually? How do we derive the vector ball phase R from the received signal R of t? Here's how you do it. This is the structure of the receiver. This is like the front end of the receiver that's going to do that for us. So let's spend some time going over this. Okay, so we have our incoming signal, R of t. We branch it out into two, we have two replicas of it on these two different branches. Let's look at the top one, and the bottom one follows in a very similar manner, so we can just focus on the top. We take the signal R of t and we multiply it by g of t and by the cosine of 2 pi fct. And then we integrate. What do we get at the end? Well, let's see, right? Let's work it out. We have the integral of g of t times the cosine times R of t, right? Now, who was R of t? Right? It was the signal that we sent plus noise, right? Now, the signal that we sent was Si in phase times g of t. You guys keep me honest here. Times cosine of 2 pi fct. Right? This is the in phase part. And I'm going to write down, just to save space, plus j, minus siq times g of t times the sine. Right? So in phase minus quadrature, right? And imagine that this goes together in the brackets, just compressing it here. And there was also noise on top of it, right? So we had this plus noise. And we integrate this over time. Okay? Everybody agrees with this? Yeah, suppose that's a yes. Now, we can break this into two integrals, right? Actually, three integrals. So let's break it. The first one is, I'm going to take the first term here on this summation and multiply it by this, right? So I get g squared of t times si in phase times the cosine squared. Okay, this is the first integral. The second one is, try to put it here, minus the integral of g squared of t. Now we have SIQ times cosine times sine. Okay, so I took this guy times the quadrature component here. Okay, and finally there is plus the integral of g of t cosine Okay, so we end up with these three integrations. So this one at the bottom, we're not going to worry about, right? This is noise. This is noise times some stuff. So this is noise. So let's call it n prime. And at this point, we don't worry about it. Come back to it later. But this is a noise term. Now let's look at the signal terms. There are two. So let's look at them. First, let's look at the second guy. So let's imagine there is no g of t here. Let's imagine for a second there is no g of t. So we only have everything else. In that case, we would have the integral. This coefficient can come outside the integration because it's constant, SIQ, times the integration of cosine 2 pi fct times the sine of 2 pi fct dt. Okay, so what is this? You guys may remember I showed you some useful trigonometric relationships a few lectures ago, right? And there was one that said that sine of x times cosine of x is equal to 1/2 the sine of 2x. Right? I remember this. So this is just the integration of a sine of 4 pi fct, right? Essentially, except for 1/2. This is the sine of twice the argument. Okay, so this is SIQ divided by 2, the integration of a sine of 4 pi fct. Okay, so as long as the integration is over an integer number of cycles, is equal to 0. Okay, so this is 0. Remember, this is the same idea we had when we were doing multipath fading, why the average of the fading is 0. You end up with an average of a sine or a cosine that is always 0. So that's 0 if there is no g. Now, we're going to put a condition on g that this integration remains 0. Okay, so let's table this for later. After the midterm, we'll design optimum g's. So the condition we want is that this integration remains 0 as it is in the case that there is no g. Okay, so we'll table that. Remember that we have to constrain g to satisfy this condition. And so this integration is going to be 0 because we're going to choose g's that meet this condition. So we'll end with this. Let's look at this term now. Okay, so now, what is this integral, this first one? Well, let's do the same. Let's imagine for a second there is no g. In that case, we have the in-phase coefficient times the integration of the cosine square of 2 pi fct dt. Okay, so what is this? Well, integration of a cosine square is equal to 1/2. right? As long as you have an integer number of cycles, integration of cosine square equals 1/2. So this is, if there is no g, this is SIQ divided by 2. Okay? So let's say we choose g such that this integration is equal to 2 times the cosine square. So let's make this, let's choose g such that this times g squared actually. Let's choose g such that this is equal to 1. Okay? Let's choose g so that this is equal to 1. And so here what we have, this integration is going to give us exactly at the end of this, with these two conditions on g, we're going to have that this is equal to SII plus some noise. Okay? So we found out by imposing two conditions on g, what we have at the end of the top integration is exactly the in-phase component plus noise. Okay, and the conditions are that this is 1, and the other was, remember, that the integration of g squared times the sine is equal to 0. Okay, so under these two conditions, we have that the top integration, the output of the top integration is exactly the in-phase component of the transmit signal plus noise. Okay, and you can go through the exact same exercise for the bottom branch, and you're going to find that at the output of the integration, we have the quadrature component of the transmitted signal S of I plus some additional noise. Okay, so this very simple receiver structure is extracting for us the two components of the transmitted vector, of course contaminated by noise. Nothing we can do about that. The noise is there. But it's doing this extraction without losing any information. So whatever information is there can still be recovered. As long as we have a good receiver here in this box that says make decision. So now we have to design this box. Okay? Questions? None. Okay, that means that you guys following very well or completely lost. So I will assume that you are following very well. If not, you'll speak up, I guess. Yes.
The church on GFT that cosine square times GFT square equals 1 that has to also mean that equals sine square GFT equals 1?
Yes. So when you're going to have, yes, exactly. So when you go to the bottom branch, so the question is, what are the conditions for the bottom branch, right? So this condition is going to be the same, right? And this one is going to end up with the sine square, right? Yeah, very good point. So at the end, the condition of the sine square and the cosine square are very similar, but you're right. So we can write another one which has a sine square here. And when you design G of t, if you meet this one, you'll meet the other one as well. But it's a good point. So rigorously speaking, we can actually write three conditions. Very good point. Other questions? Okay, so you guys can jump in anytime you want with questions. Okay, so this circuitry is extracting for us these two components of the transmitted vector plus noise. And now we have a box that says make decision, which is what we're going to talk about. Now, how do we, if there was no noise, this is trivial, right? If there was no noise, you're finished. You know exactly what was sent. You know, a perfect receiver. Now, because there is noise, you're not finished yet. Now you have to use this information to actually make a decision. So how do you do that? Well, before we do that, let's elaborate a bit on this structure because this is the, this is the cornerstone of a receiver. What happens if the transmit signal has only in-phase component? Well, in that case, we have the same received signal as RFT, except that in the quadrature dimension, there is no signal, there is only noise. Okay, so we don't send anything, so all we receive in the quadrature dimension is noise. So in the textbook, that's called a remainder noise. And it has no effect on the detection. Right? If you think about it, we didn't send the quadrature signal, so we're not going to look for it. So whatever noise is in that dimension doesn't bother us, because there's nothing there to be found. Okay, so in that case, the only thing that matters is the in-phase noise. Now, there is an alternative form for the receiver that we just saw, which is the one that is actually implemented, which is this one here. And let me take you through the equivalence, because it's not in the textbook, and it's not hard, but let's make sure that we follow. So we're going to go from here, we're going to go to here. Okay, so what we're going to do is go backwards in some way. First of all, let me show you what was changed here. We had a cosine and a sine. Now, we don't want to have two different oscillators in the receiver to have to generate these signals. So what we do is we generate a cosine, and then we just advance it by pi over 2, and that gives us a minus sign. Okay, that's how it's done in practice. You have a single oscillator that gives you cosine. Then you advance the phase by pi over 2, and you get minus sign. Okay, so that's the first change between these two structures. Very easy. And the second one is a little more involved. So we're going to replace this product and integration. So here, okay, notice here, we multiply by g of t and the cosine. And here, g of t and minus sign. Now here, I'm multiplying only by the cosine and the minus sign. So the multiplication by g of t has disappeared. And the integration has disappeared. So this has been replaced by a convolution with a filter and sampler. Okay? So now let me go backwards and show you that this is exactly the same as this. Just a more practical way of building it, but it's exactly identical. Okay? So the idea is to do a convolution with a reverse version of G. Now let's go through that. What's a convolution? Yeah, it's exactly. Convolution is integration. Now, what do we integrate? Well, so let's take this convolution and write it down and try to turn it into the integration we had in the previous page. So we have the integration of r of t prime. I'm going to use t prime to denote the integration variable times the cosine. Notice that I'm multiplying by the cosine still. We're here. 2 pi fc t prime. And now I'm convolving this with g of capital T minus t. Okay? So the convolution entails that I use, okay, so g of t is, now to convolve, I have to integrate these by replacing this one, t minus t prime, t prime. Okay, so let me recall what's the convolution of, let's say we have two functions, x of t and y of t, and I want to convolve them. Okay, how do I write this down? It's the integration of x of t prime times y of t minus t prime, t of t prime. Okay, t prime is just a dummy variable. I integrate over it, and it integrates out, and the output is a function of t only. Okay, so I'm using the same formulation here. So I'm taking the first part of the convolution is what comes into the filter. It's r of t times cosine. And this is the second part of the filter. Okay? So that's the output of the convolution. Now I'm going to sample this at time capital T. So what that means is that I'm going to evaluate this when T is equal to capital T, T sub s, to be precise. So what do we get? Integration of r of T prime times the cosine. Okay, now times g of, as you can see, the capital T's cancel out, and I'm getting just g of T prime, d of T prime, right? So capital T here cancels capital here. I get a sign flip, and I get a positive T prime. And this integration is exactly the same as this integration. Okay, it's r times g times cosine integrated, r times g times cosine integrated. Okay? Any questions in these equivalents? Right. The integration should be over all the time span on which g is non-zero, right? So I'm using here the notation of the textbook, but your point is very well taken. The integration should be actually possibly wider than that. So if g spans more than 0 to t, then the integration should go wider than that. And in general, that's the case. So it's a little bit, I think it was meant for clarity, but it may be confusing at the end. So that's why in my integrations, I'm not putting any intervals. So that, what I'm meaning with that, by not putting integration limits, is integrate whenever g is non-zero, essentially. And that may be beyond 0 to capital T. By the way, this should be T sub s. I apologize for that. Forgot the subscript s here. But anyway, I'm sure that's clear. But it's a good point. So the integration should be over the whole time interval where g is non-zero. And for this type of pulses that we show here, right? If you have this, then that's fine. 0 to t is fine. But you may have pulses that are wider than this. In fact, usually you want to have them wider. So the integration might extend to a bigger time interval. Very good point. Other questions? Okay, so now we know how to extract this vector. Now we have to learn how to make a decision here. So how to use this vector to figure out which of the points in the continuation was actually sent. Well, we want to minimize the error probability, right? We want to choose the best possible. We want to make the best possible choice so that the probability of making an error is as small as possible. So we don't know which of the points, which of the capital M points S sub I was sent. All we know is what we receive. We receive R. So what we're going to do is we're going to choose we're going to decide for the S sub I that has the largest probability, right? So we're going to say, okay, which is the S sub I point for which the probability of that point being sent, given that we receive R, is bigger than for any other points. That makes sense, right? That seems reasonable, right? Of all the capital M points, we're going to choose the one that has the biggest probability of having been sent, given that we receive a particular R. You're going to do better than that, right? That's the point that has the best chance of having been sent, by definition. Is that clear? You guys think this makes sense? That's right. So given that we don't know for sure because there is noise, this is the point that has the biggest probability of having been sent. So how do we make these decisions? We're going to define the set of decision regions called by Z sub I. So Z sub I is going to be the region of all possible received vectors R for which the probability of S sub I having been sent is bigger than for any other point, right? So the index I here corresponds with the index I here. So for example, Z sub 1 is the region of all the points for which the probability that S1 was sent is bigger than the probability that S2 was sent, or S3, or S4, or S5, given that we receive a particular R. Okay? So these regions partition the signal space and are non-overlapping. So what does this mean? What this means is that every point R, every received vector R, is going to be in one and only one of these regions. Okay? So every point has to be in one region and only in one region. So there can be no points that belong in no region. Okay, that's a very good question. So the question is, can the probabilities be equal? The probability of S1 having been sent to S2 for a given R. Yes, they can be, right? So this is a very good question. Let's imagine we have and this is actually a very practical case, right? We have a constellation with 4 points. This is the most commonly used constellation, so we're going to study it in more detail. It has 4 points in the complex plane. This is I, and this is Q. And the decision regions are very easy here, right? All you have to do is partition these. Actually, no, it's by quadrants, right? So this quadrant, imagine the 4 points have the same probability, right? So this quadrant is the decision region for this point, right? So if R falls in this quadrant, we're going to choose this guy, right? Now, what happens if the point is exactly on the line here? That's your question, right? Are we going to choose this point or this point? They have the same probability, so we don't know. So we can arbitrarily assign the line itself to any of the regions. Because if the point is exactly on the line, it has a 50% of being either one. Now, what happens is the following. Because the noise is Gaussian, the probability that the noise, so this is interesting, right? When is the received vector exactly on the horizontal axis here? When the quadrature noise is 0, right? When there is no noise in the Q component. So now, what's the probability that the quadrature noise is 0? Is 0. Is 0. Right? Because a Gaussian function never touches 0. So essentially, the point is that this is never going to happen, right? But if it did, for example, you could have other types of noise for which this can happen. Definitely. So in that case, you have to make an arbitrary choice. You toss a coin and you say, okay, this guy or that guy. But the formulation doesn't help you here, because when the probabilities are exactly identical, both points have the same probability, so you can choose one or the other. Unfortunately, this doesn't happen because the noise is Gaussian, but it could happen with impulse noise, for example. This could happen. So it's a good question. Other questions? Okay. So as we said, the space has to be partitioned fully, so all the points have to be in one of the regions, and in only one of the regions. Now the receiver is going to decide for the constellation point on whose region the receiver vector lies. Right? For example, in this case, if the vector falls in this quadrant, we're going to choose for this. We're going to decide this was the point that was sent. Now, if all the points have the same probability a priori, this is tantamount to deciding for the one closest to the received vector in distance. Right? And this is called the maximum likelihood criterion. Choosing the one that's closest is called the maximum likelihood criterion. And this is intuitive, but I'm going to now show it to you rigorously. But it's intuitive, right? So in this case, in any case, right, I take a point and I look at the closest, I take a received vector, say, okay, my received vector was here, right? The closest point is here, so I'm going to choose for this point. Now, this is only true if the 4 points have the same probability, right? Otherwise, I can't say, right? Imagine that this point is much more probable than this point. then I'm not sure anymore, right? But usually the points are equally probable. So, and in fact, for this course, we always assume that the points are equally probable. So in that case, this is true, and one can actually show it rigorously. So let's go through it. First, we can use Bayes' rule, and probably most of you have seen Bayes' rule. It allows you to express the a posteriori probabilities based on the a priori probabilities. So essentially, it tells us that the probability that S sub I was sent given that R was received is equal to the probability that R was received given that S sub I was sent times the probability that S sub I was sent divided by the probability that R was received. Okay, this is a Bayes rule for a posteriori and a priori probabilities. So we want a receiver that maximizes this probability. Remember, that's our rule. We want to maximize this guy. So this is equivalent to maximizing this guy, since these are equal. So as it turns out, this denominator, right, does not depend on I. So it's the same for all of the possibilities. So we can just forget about it, right? In other words, maximizing this ratio is equal to maximizing the numerator, because we maximize over I, and here there's no I. So that's simplifying things for us a little bit. So now we only have to look at this product. Now, under the assumption that all the points have the same probability, the probability that S sub I was sent is 1 over capital M, right? There are M points. Each one has probability 1 over M. And so this also disappears from the utilization. So now we're left with this function. We're going to maximize this guy. Probability that R was received given that S sub I was sent. So we give this a name. We call it the likelihood function, L. Now, who is this guy? Well, remember when we saw the review of probability theory, that if variables are independent, the probability is factor. Okay, the probability of the joint is the product of the separate probabilities. Okay, so now who is the random variable R given that Si was sent? Well, it's easy, right? If Si was sent, R is equal to Si plus noise, right? And Si is fixed because we know what it is, whatever was sent. And this is Gaussian noise with zero mean. So this R is also Gaussian with mean S sub I. Remember, when we take a Gaussian variable and we add a constant to it, we get a variable with the same variance and the mean shifted by this constant. So the mean was 0. So now the mean, right, this is a Gaussian variable with mean S sub I and variance, the variance of the noise, which was n sub 0. Okay, so this means normal Gaussian. S sub I is the mean, n sub 0 is the variance. So that's the variable R given that S sub I was n. Now, the in phase and the quadrature components are both Gaussian, real Gaussians. And so what's the PDF of this variable? It's this Gaussian here. It's a two-dimensional Gaussian, right? So it's the product of two one-dimensional Gaussians. So we have, for the in phase, we have 1 over square root of 2 pi times n0 divided by 2. So the variance is n0. So it's n0 divided by 2 for the in phase and n0 divided by 2 for the quadrature phase. Okay? Times e to the minus, let me see the notation. And here twice the variance. Okay, so this is 1, and then times the other. Okay. And here we have okay, so these 2 cancels these 2 cancels these 2. So we get square root of 2 pi times square root of 2 pi gives us the 2 pi. 2 pi times n0 divided by 2 This is inside the square root, I'm sorry. Okay, so this cancels this. The exponentials come together and you get this. So this is a two-dimensional Gaussian. This is just the product of two independent Gaussians, one for the in-phase, one for the quadrature. Okay? So this is the magnitude function, and when the receiver has to maximize. So remember, we came from here using Bayes' rule, and then using the fact that all the messages have the same probability, we end up they want to maximize this function. Okay? Now, maximizing this, we can forget about this factor, right? In terms of maximizing, doesn't matter because it's just a constant. We can drop this. Now, the exponential function is monotonic. So maximizing an exponential is the same as maximizing the exponent. In other words, if you maximize the exponent, you're maximizing the exponential. So we can forget about the exponential also and maximize the exponent, which we call by mu naught L. So mu naught L is the exponent of this, of the capital L. So we found that we have to maximize, the receiver wants to maximize this exponent. Now remember, we saw a few minutes ago the notion of distance between two vectors. This is exactly the distance between vectors r and s of I. Okay, is the square. So this is distance squared. So essentially, we've shown that the optimum receiver chooses the s of I that is closest to r, right? Okay, we want to maximize this. Notice that this is negative, right? This is a negative function, so we want to minimize it. Okay? So to maximize this, we want to minimize the distance, okay? Because there's a negative sign here. So minimizing this, I mean choosing the point that is closest to the received vector r, which is what we saw intuitively. Okay, so we've seen rigorously that under the assumption that all the points have the same probability, the optimum receiver has to choose the point, decide for the point that is closest in distance to the received vector r. Okay? If the constellation points are unequally probable, then this would not be true anymore. And then we'll have to reshape the decision regions depending on the probability of the corresponding points. So we're not going to deal with that, but just keep always in your minds that all of this is only true if the points are equally probable. So a trivial case. Here we have a modulation with 2 points. A point called capital A and a point called minus capital A. So the decision regions are 2. The first one is Z1. Okay, let me draw that. Yes. So this is a one-dimensional modulation. Here. So it's on a line. So there is no quadrature, there's only in phase. This is 0. We have 2 points. One is here, capital A. The one is here, minus capital A. So the decision regions are, one of them is all the positive values, right? And the other one is all the negative values. So if the received vector is positive, we choose for capital A. If it's negative, we choose for minus capital A, right? So this is a trivial case. But it actually corresponds to a modulation that is called BPSK, which we're going to study. Questions? Okay. One last notion and we'll wrap it up. Okay, you know what? This is a very long section, so we're going to just leave it here. And you guys have a good week. As I said, we'll post the solutions for a couple of problems, 3 or 4 problems on what we saw today about frequency selective channels, capacity and stuff. So if you guys choose to, you can practice a little bit. And the part that we saw after the break is not going to be part of the midterm. And I'll see you next week. Okay? Questions? The question is if the midterm is going to be gears more towards the stuff covered mainly. No, I should cover the first 4 chapters especially chapters 2, 3, and 4, I would say, because the first chapter is just introduction. 2, 3, and 4, so propagation, and information theory. Right. Okay, have a good week, guys.